Confidence intervals allow us to say that using our sample, we're 95% confident that the population accuracy P is in the interval 0.72 to 0.88. 0.72 is called the lower bound and 0.88 the upper bound of this interval. The calculation of these confidence intervals is beyond the scope of this course, but it's important to understand their interpretation. When we report the accuracy of a model on the sample, we report it with the mean and the confidence intervals. The 95% confidence intervals here allow us to say that with 95% confidence, P is in the interval 0.72 to 0.88. What we haven't seen is what it means to be 95% confident. 95% confidence does not say there is a 95% probability that P lies within the interval. It also does not say that 95% of the sample accuracies lie within this interval. The interpretation of 95% confidence is a little more nuanced and requires us to think about making repeated samples. Let's dive into this. Let's say we were able to repeatedly sample 100 patients from the population several times. Each time we get a different sample and hence a different sample accuracy. We can also compute the confidence intervals associated with each sample. We can look at these samples on a plot. For each of these samples, we can plot the sample accuracies, here represented by the circle, and the lower and upper bounds of the confidence intervals of the samples. On this plot, we also have the true population accuracy plotted as the dotted line. This is unobserved. Note that most of these samples contain the population accuracy, this vertical line. Here 6 out of the 7 contain it, and 1 misses it. In fact, when we have 95% confidence intervals, 95% of these samples will contain the population accuracy. 95% is what's called our confidence level. Thus, the interpretation of 95% confidence is that in repeated sampling, this method produces intervals that include the population accuracy in about 95% of samples.